In this video, we're going to look at how to build an activity series for a redox reaction using experimental data. So what would an experiment look like that we could use to build an activity series? Well, the simplest iteration would be having some sort of container for solutions containing various metal ions or non-metal ions, and then having in the case of metal ions here, having the counterpart elemental metals, and testing that metal with the various ion solutions. In this scenario, you'd be looking for evidence of a chemical reaction. And what is evidence of a chemical reaction? Well, it includes things like color change, temperature change, bubbles, the formation of a precipitate, change in pH. Any of these can tell us a reaction has occurred. Typically, we're going to be doing single displacement reactions, and we'll be looking for things like color changes and the formation of a precipitate. So, we're going to go through two examples of how we can present this data. So the simplest example is in a table. So how this table works is we have our metal ions at the top, and then we have the corresponding elemental form of the metal down the bottom. Now, obviously, these are just made up metals. There's no element A, there's no element D in the periodic table. Along the top, we have our metal ions. These are oxidizing agents, meaning these ions will undergo reduction in these reactions. That means that along this left side, we have our reducing agents. Elemental metals tend to be reducing agents, and reducing agents will undergo oxidation reactions. What we want to consider now is the number of reactions that occur. So with an oxidizing agent, the more reactions that occur, the stronger that oxidizing agent is. The fewer reactions that occur, the weaker that oxidizing agent is. We could do the same with our reducing agents. So again, the more reactions that occur, the stronger the reducing agent, and the fewer reactions that occur, the weaker the reducing agent. So an easy way to kind of tally or to organize our data is to take a tally of how many reactions have occurred. So A plus has undergone 4 reactions out of the 5 possible. B2 plus has undergone 2 of the 5 possible. C3 plus has undergone 1 of the 5 possible. D has undergone all 5. E has not reacted at all. And F2 plus has undergone 3. You'll notice these dashed lines along the diagonal. We don't need to react a metal ion with its elemental form, as it's not going to be a spontaneous reaction. And so that just saves us some supplies as we do our reactions. We can do the same thing for our reducing agents. Just tally how many reducing agents react. So A solid underwent 1 of 5 possible reactions. B solid had 3. C solid had 4. D had none. E had all 5. And F had 2. And what we can notice here is that the numbers kind of switch. So where E didn't react at all as an oxidizing agent, it reacted 5 times as a reducing agent. Where D reacted 5 times as an oxidizing agent, it didn't react at all as a reducing agent. And so we can take the number of reactions that occurred here and rank our oxidizing agents from strongest to weakest. So the strongest oxidizing agent will have the most reactions, and the weakest oxidizing agent will have the fewest reactions. And I'll just add OA there because we're going to do the same for reducing agents. So now we can do the same for reducing, and we see that our weakest reducing agent had no reactions. running out of room here. Weakest reducing agent had no reactions, and our strongest reducing agent had 5 reactions. And we can see that our strongest oxidizing agent also corresponds to our weakest reducing agent. So once we have these ranked, we can start to build ourselves a table. And so we see this table here, and what we see is that D3 plus had the most reactions. It is our strongest oxidizing agent, and so it's going to be in the top left. Strongest oxidizing agent, it's the top left of this table. The fewest reactions was E plus. It's at the bottom of the table as the weakest oxidizing agent. Our strongest reducing agent is E solid. It underwent the most reactions. You can see here. So it's at the bottom right of the table. And then our weakest reducing agent, D solid, is at the top right. And so we have these half reactions, all reduction reactions, going from strongest oxidizing agent to weakest oxidizing agent going left to right, and from strongest reducing agent to weakest reducing agent going from right to left. We can also build a similar table with lists, and this is a little bit conceptually tricky because it requires us to visualize what's happening. So here we're given 3 reactions, and we're told whether or not there is a reaction. So the first reaction we see is spontaneous, as is the third, and the second reaction is non-spontaneous, so no reaction occurs. And the first thing we're going to do here is we're going to just highlight which of these reactants is an oxidizing agent and which is a reducing agent. So oxidizing agents will be gaining electrons. So if we look at our first reaction, we have C4 plus in our reactants and C3 plus in our products. And so cerium here gained 1 electron. Copper goes from copper plus to copper 2 plus. So copper lost 1 electron. And so what we can determine from that is that cerium 4 plus is our oxidizing agent. It was reduced. And copper plus was our reducing agent as it was oxidized. And we can do the same for the next 2 reactions. So here we see cobalt 2 plus is oxidized. It loses an electron to form cobalt 3 plus, so that's going to be our reducing agent. And cerium 4 plus will again be our oxidizing agent. And in our final reaction, copper 2 plus gains an electron, so that is our oxidizing agent. And manganese solid is our reducing agent. So now that we've sorted out oxidizing agents and reducing agents, we're going to remember our key fact. For a reaction to be spontaneous, on our activity series, the oxidizing agent must be higher or must be above the reducing agent. So we're going to go through each of these reactions. So for the first reaction, we know that cerium 4 plus is higher on the table than copper plus. And so we could start to build this table out by just listing cerium 4 plus, and then somewhere down below on the opposite side of the table will be copper plus, because copper plus again is the reducing agent. We can go to our next reaction now, and we know that cerium 4 plus does not react with cobalt. So that tells us that cerium is lower on the table than cobalt 2 plus, which is the reducing agent. So cobalt 2 plus will be somewhere up here above cerium. And we're going to leave some space in case there's anything that slots in between. So we know cobalt is above cerium, cerium is above copper. And we can look at our last reaction now, and we see that copper is capable of oxidizing manganese, meaning that copper will be above manganese on our table. So again, copper 2 plus will be on the same line as copper plus. They're part of the same half reaction, and so manganese must be lower down. And so this might look a little haphazard because we are missing a bunch of things, but we can fill in the missing gaps. I'm just going to use a different color here so we can see the difference. So where we have cerium 4+, cerium 3+ is on the opposite side of that table. Where we have cobalt 2+, cobalt 3+ is its counterpart in these reactions. Where we have both coppers there, and then we have manganese 2+. And so we can start to see that we've built a reaction table. Now we haven't written the full reactions out. We'll do that on the next slide. But we have our strongest oxidizing agent in the top left and our strongest reducing agent on the bottom right. And so here we have the full reactions. And so all we've done is we've added electrons to balance them. And we're always going to write these as reduction reactions. So going from left to right here is reduction. And so if we were to go back to our data, cobalt is our strongest OA, and so therefore our weakest reducing agent. It was not capable of reducing cerium. Cerium was capable of oxidizing copper, and copper was capable of oxidizing manganese. And so we have this full table, and we could do this with more reactions, or we could try to put this into an experimental data table form if that's easier for us. But we have now two ways of solving this type of question.